So today I'll be talking how we put the theory we covered over the past 2 days into practice. So as I said, prepare for very few equations, lots of pictures, lots of thinking about practical problems. Also, from now on, this lecture is moving beyond the free references I gave you. So the theory part was based on the paper by Narayan and Bartleman, a bit on the SASFI lectures, and a bit of Massimo Meneghetti's lectures. These are from 1995, 2003, and 2006, respectively. All of these are new results from the last few years, mostly. So these are taken from papers. Some of them will be on the list for presentations. Some of them are just stuff that has been published over the past few years. I used a decent number of slides from other people from conferences, so I'll try to pay due credits each time I show something. But basically, as I've been saying for the past 2 days, think about RxJ1131 with its lensing galaxy, a small satellite, 3 strongly lensed quasar images, and the Einstein ring that you can't see anymore, and the cosmic horseshoe that you can't see anymore either. So these are all, okay, this is starting working. So these are 2 cases where we have lensing by a galaxy or very few galaxies. But also clusters are actually very powerful lenses, and this is the Smiley cluster. As it brightens up, you will see some very nice Einstein rings. So there's an arc here that you might see very faintly. There's a faint arc here, faint arc here. So these are all done with HST. As we derived yesterday, HST has very high resolution on the order of 50 to 100 milliarc seconds. In other wavelengths, this gets more difficult. But for example, in millimeter waves, as we saw yesterday, ALMA provides even better resolution than HST, and this is SDP81, observations taken in 2014 with very high resolution ALMA configuration. And you see this very nice structure of the source. And you can go to even higher resolutions, and you go something like the global VLBI, a network of radio telescopes spread across the entire Earth. And this is probably the nicest VLBI image that I've shown already on Monday from Cristiana Spignola, and you see these very fine Einstein arcs with some structure in them. This is a lensed AGN jet. The resolution here is on the order of milliarc second. Just to put this into perspective, this entire thing is maybe 1 arc second across. This is absolutely crazy quality. So why do we care about gravitational lensing apart from the tests of general relativity, where we did one? They are good for looking far because they brighten up very distant galaxies. They allow you to look into details of these galaxies because they make them larger. And also, unlike with the normal telescope or a magnifying glass, the problem we have with the lenses is that, with the gravitational lenses, is that the glass you are looking through, the mass distribution of these galaxies, is complicated, and we don't know it. In telescope, you know what lens you put in, what mirror you put in. Here, we don't know it, but it's interesting in itself because it tells you how massive the galaxies are, how does their mass vary. So we have basically these 3 distinct issues, and I will try to go through them one by one. But in principle, what you really need to keep in mind is that if we, for example, want to see the source as it really is, we somehow need to reconstruct it from these lensed arcs. And again, in a telescope, you would know how your optics looks like. Here, you have to also solve for the optics that you are looking through. And this is a non-trivial problem. So what do we need for that? We need high angle resolution because here is one of the lenses that I've seen before, the Einstein cross. It's only a few arc seconds across, so HST can do it. ALMA can do it. Actually, this number of telescopes can resolve this, but it can't do it with a very small telescope. The separation of the images is few arc seconds for lensing by galaxies. It is more when the lens is a galaxy group or a cluster. And yesterday's exercise number 1, where we derived the resolution of different telescopes, gives you some idea whether we can use them for this exercise or not. And the point is, most of them can do it. So what we can study in the source, so this is a galaxy NGC 628 combination of AGST and ALMA observations. So they have stars. Here we have to think the galaxies in the background that we want to study, the source galaxies, are redshifted from us. They are at large distances. So typically the stars you can access at high resolution with Hubble Space Telescope, Very Large Telescope in Chile, CAC in Hawaii, for example. You can go for spectral lines, and at high resolution you can study them with the VLT and CAC because they move slowly from optical to near infrared. There is often in the center of these galaxies, there might be an AGN, an active galactic nucleus with synchrotron emission. You can study that using VLA, Very Large Array, the Global Very Large Baseline Network, eMerlin, different radio interferometers. You have dust in these galaxies. That's where ALMA or NOIMA in Europe, the millimeter wave interferometers provide high resolution sensitivity. You can study their molecular gas, typically traced by the CO emission. Again, this can be done with ALMA, NOIMA, VLA, or if you want to do something more difficult, you can go for much weaker emission lines, and we'll see later that we can really do this. For example, HCN, which is a molecule that traces a very dense gas just before it starts forming stars. And this can be done with ALMA, and we are now trying to do this in VLA systematically. So going back one slide, if we want to figure out how does our source look like, we need to get rid of the lens in front. We need to know how are our images deformed. So do we have enough constraints? So consider a case we had yesterday, which is where we have a single isothermal ellipsoid now, because as we saw yesterday in Caps log, normal galaxies are not spherical. They're almost always elliptical, and indeed, you need an elliptical galaxy to get these 4 images, as we saw yesterday. So just take a singular isothermal ellipsoid and a point source, and the question is, how many degrees of freedom do we have? So we have a singular isothermal ellipsoid, and we have a point source somewhere. So the lens gives us these degrees of freedom. Where is the lens located in the sky? That has 2 degrees of freedom, the x and y coordinate. What is its Einstein radius or mass for the singular isothermal ellipsoid? So that's 3rd degree of freedom. It's elliptical, so how elliptical it is? So that's your axis ratio. And how is it oriented in the sky? Is it upright? Is it like this? Is it somewhere in between? So it's the position angle of your ellipses. So just the lens model needs 5 parameters to be constrained. Then the point source comes with 2 more degrees of freedom, because now let's say we know where our lens is and how it looks like, but where is our source? Is it over here, right behind the lens, somewhere else? So for a point source, we have 2 degrees of freedom coming from the position of the source. And also we know how bright the images are. And so there is a final degree of freedom, the source flux or the source brightness. And it comes with a question mark that I'll explain in a few slides. Normally for point-like sources, you will discount this because it's very sensitive to obscuration, to any intervening mass. But we have these standard 7, maybe 8 degrees of freedom we need to constrain. Do we have enough constraints? So let's keep 8 degrees of freedom. here we have the 4 image system we saw before. So how many constraints do we have? Well, for each, so we have 4 images, and each image comes with its own position. Whether it's over here, or over here, or over here, it makes a difference. So we have two constraints for image based on its position, and an extra constraint from the flux of each image. So that gives us 12 constraints if we consider the fluxes, 8 degrees of freedom if we consider the flux as well. I mean, that's pretty good, right? We have more constraints than variables. That looks pretty good. But image fluxes are not always reliable for point-blank sources. And why? As we saw yesterday, the time it takes the light to reach each of these 4 points from the source can be different. It's the time delay surface we were talking about yesterday. So if your background source is variable, you see it in different points of time, and the fluxes will not match. You can have microlensing by stars. I'll talk about it tomorrow, but basically if you have a point-blank image, if there's a star passing in front of it, it can introduce extra microlensing on top of what the main lens is doing. So these might be actually perturbed to what you would expect from a nice, smooth lens. And finally, there is dust in galaxies. So what can happen is if one of the images passes through more dust than another image, this one will become dimmer than the other one. So often we basically get rid of the fluxes completely, but then we still have 2 positions per each image. That's 8 constraints for, now we would have 7 degrees of freedom because we don't consider the source flux. 8 constraints, 7 degrees of freedom, pretty good. But then it gets more complex, because what if there is a nearby galaxy? And we often see that we need to take even pretty distant galaxies into account. In that case, you can simplify the problem, because that galaxy over here might only contribute a little bit of shift in image positions in one direction, but that's already 2 more degrees of freedom. Which direction and how strong of a shift? And maybe, singular isothermal ellipsoid is a very simple model. Maybe your lens is not that, and then you need to put extra degrees of freedom on top of that. But let's think now about, okay, let's keep the 12 constraints to 80 degrees of freedom, the best case scenario we have. So how we would go about this? And you've seen this plot, I think, 2 or 3 times already. These are our rabbit images in the gravitational lensing. And as we saw before, this is the viable configurations where the 2 rabbits are flipped in the tangential direction, but not flipped in this direction. And if I would zoom in on them a bit, here you see the rabbits. And now we can think, the ear over here is the same bit of an ear as over here. The leg down here has to come from the same position as the leg here in the source plane. Now the front leg, now the tails. And so if you have more extended lenses, in this way you can basically build up a series of points that you can use to constrain your mass model. Assuming you can distinguish that, okay, this is a front paw, this is a front paw. And this is the first lens modeling technique that I'm not sure if it has a proper name, so I call it tagging. So basically what we had yesterday, also these image configurations, you have a single source here, let's say the red point. It maps into 4 images over here. The blue point over here will map into 2 images over here. So basically this thing and this thing, given the lens model, has to go back to only a single point in the source plane. And again, think of the rabbit. If you have the more complicated your source is, the better, because you have more constraints. I have front leg, back leg, tail, ear. I could maybe do the nose. What else can I do? Maybe the part over here where the ears start. So you can build up the number of points that have to map to a single location in the source plane. And this is, for example, how this lens was modeled. So you see this exquisite Einstein arc here, but you see a lot of structure in these images, especially here. So you have a kind of a thing, I should have zoomed in, but there's like 1, 2, 3, 4 blobs here, 1, 2, 3, 4 blobs here. There is a blob here, blob here, blob here, blob over here. There is another image here that corresponds to this thing. So what I did in the paper by Spignola et al., you go, this is your lens, and you try to find the parts of the source that go into individual images. So there is an image number 1. It is seen here, okay, A1, B1, C1, D1. They take image number 2, they find component number 2, so it's A2, B2, C2, D2, and so forth. And then this is very small on this slide, but basically when you do the lens modeling, you see they all lie on a line. And this is kind of what we would expect, because what is happening here? We have a galaxy, and there's an AGN jet coming out of it, and jets are typically pretty straight. So basically it's not a surprise that all of these points map onto a straight line. But this means, so this technique works, is pretty simple. There are some publicly available codes how to do this. But it works if you can identify components of different images that go together. So now I have a very nice rabbit that has ears, legs, tails, and tail has to go to tail, etc. So this, you can see it by eyes. But this could think, if you would just plot this lens like this, or if you consider RxJ1131, you can't. They are kind of a mush. They have these nice Einstein rings, but it's hard to identify individual components in them. So what we want to do is to have a technique that allows us to use extended structure of the source and do this mapping not by hand, but sort of automatically. Because here we really had to by hand pick individual components. This lens had lots of structure. If you go to something like this, it's hard to say this point, where does it go? This point, where does it go? And sure, we have the 4 images here, but we also know there is a second small lensing galaxy inside, so the number of constraints here gets small. And so what we would like to do is to somehow do this for extended, complicated sources. And now comes a bit of a very simple math. So imagine I have some source, and I can describe it as a matrix. I can in the source plane make a pixel map, x, y. Here is my source. It's brighter over here, and you have some matrix that describes the source surface brightness distribution. And then, if you know your lens, you have the lensing equation, which is beta equals theta minus delta phi. Lensing potential, you can of course invert it. You can do this. So you can take this and you can lens it forward. So what you can basically do, if you know your source and you know how your lens works, you know how your sky is going to look like. For example, like this. This is a source. We put some lens into it, and it makes a nice sky image. And then if you want to compare this to the real data, all you have to do is add some noise on top of it, because data is noisy. And for example, for optical telescopes, we know we don't have infinite resolution. We have the point spread function that is dictated by the construction of your telescope and its size. So just smear your data by it. And so this is in principle a pretty neat equation. On one hand, basically, if you know what your lens source looks like, you know your lens. The PSF is dictated by the telescope. Here is your noise. You should be able to reproduce your data. And so if you want to do this extremely brute force, you can just do, you can do Monte Carlo or a similar approach and just brute force, try to change your source and your lens model until you match your data. Well, that has to be done in a slightly. So how do we do that? We need a good description for the lens, because if the lens and the source can take whatever form, this is super difficult to do. But we know that lenses typically come with some mass density profile, like a singular isothermal ellipsoid that we discussed yesterday. But what about the source? So we have two options. We say, well, a lot of galaxies look like, let's say, a Cerseic profile, or maybe even like a Gaussian in the sky when you look at the light distribution. So maybe our source is just going to be expressed as an analytic function. The nice thing about it, it's simple. It gives you a lot of constraining power, because you already tell the system, you already tell your code, this is how we expect the source to look like. So it's going to give you a lot of constraining power. But if you have high resolution observations or complex sources, this is going to be too simple. Or you say, okay, my source is not going to be an analytic function, it's going to be an array of pixels, like you would take with an image with a camera. The thing is, it can deal with complex sources, but it can really fall apart. And just to show one of the techniques, how this works, this is a pixelated technique by Warren and Dye from 2003. So what they have here is they simulated observation. So they create some fake source. Now it's composed of two blobs. One blob, second blob, it's pixelated. They lens it forward. They lens it forward, they add the noise and the PSF, so they create a fake observation, and they try to solve the equation we saw before, and what they get is a source that looks like this. And that's pretty good, because what they needed to do at the same time is constrain their lens. In this exercise, they say, we don't know what the lens looks like, we need to solve for it. And they get a source that looks very much like what we would expect, or what we put in. So how about we apply this to RxJ1131? So this is the equation we need to deal with. There is a source, lens, and there's a bunch of things we know. We know the data because this is what we observe, let's say from the HST. The PSF is coming from the telescope. So for the HST, it's in the space, there is no atmosphere, so it has a very well-constrained PSF, the point spread function. If you are doing ground-based observations, you also have the atmosphere and the seeing issues, but you can still get your PSF model, for example, by observing a very bright star, which should be a point light from your telescope, but because of atmospheric seeing and the telescope design, it might end up being, looking something like this. So this can be extracted from the data as well. The noise, you can just measure it from the data. That's not difficult. So you have these two unknown things. But we can say that lens is a single isothermal ellipsoid. Let's do that assumption and have a pixelated source. And when you use this approach and run it on RxJ1131, the source looks like this. Uh-oh. This is almost exactly like our lens looks like, except the noise is gone and the PSF is removed. And our source looks like this. Uh-oh. So what the heck happened here? The problem here is that for this equation, if you remove the lensing, it's a perfectly fine solution. Because then you have some source, very complicated, you just smear it by the PSF, you add noise onto that, it matches data perfectly, and there is no lens to deal with. So then that's why a source like this is a fake RxJ1131 source, there is no lensing, we just observe it with the HST, it looks like this. It's a perfectly fine solution for a pixelated model. But we know it's not very physical, because we would have 4 quasars at the same redshift, and the time delay between them is on the order of few days. So you would have 4 quasars that are thousands of light years away from each other, who are somehow synchronized to within few days. So we need to find a way how to get around this, which is we either need to restrict the source structure, or we need to put some constraints on the lens mass model. What went wrong here is that I didn't put any constraints on the lens model, and then it says, okay, 0 mass. Perfectly fine solution, 0 mass, no lensing, we are done here. Or we can say that, the source can't be any random array of pixels, it has to have some particular properties. And just to reiterate, this can also happen in a tagging approach, because now we tagged all the the tail here, leg. Here is a lens, but a perfectly fine solution is no lens, 2 rabbits. So how we fix these issues that the lens can have 0 mass? Well, you can put some priors on your lens parameters. So one good thing is to say it cannot have 0 mass. And we also, from observations, for example, in RxJ1131, we can make some educated guesses, right? The image separation is roughly 2 Einstein radii, as we saw on day 1. We see the lens in galaxy, so we know roughly where it is in the sky, and maybe if you want to trust it, you can measure its axis ratio and say, okay, my lens should have axis ratio of roughly something like that. So this already puts some constraints on your model. Or you can introduce what is so-called the penalty function. So these are images I took from the Galaxy Zoo, from the SDSS survey. And you can't see much happening here. But basically what you are supposed to take from this is, this looks like a sort of blobby with some bright stuff in the middle, blobby with some faint spiral arms, but they are not, they're kind of smooth overall. So what you can say, my source has to be smooth to a certain extent. And what you can do is say, if the differences between the values of neighboring pixels in my source are too large, I don't think this is the correct solution, and you penalize this solution. So you don't minimize only the chi-square, you put some additional term in to make sure that you can't have one super bright pixels and next to it a very faint pixel. So when you do this properly for RxJ1131, you get something like this. So this is just taking one filter from the Hubble Space Telescope. This is a model done by Sherry Suyu, and here you see the resulting source. There is very bright pixel in the middle, that's the quasar, but then you see this extended emission with some blobs. If you really believe in it, there is maybe some sort of spiral arm structure over here. So this is how the optical emission from your RxJ1131 looks like. Yes?
Will be that different configurations of lenses and IPF, SPF give the same results?
Good point. You mean the same looking source, or a different combination of a lens and a source?
Different combinations.
Yes, that's a problem. Okay, I didn't include it in my slides. So a lot of that depend. You can make your lens more complex or less complex, and that would change how your source looks like. What you can also do, it depends really on how you, if you are, let's say, saying I'm penalizing this amount of structure in my source, that I can't have big differences between pixels. There are a few different ways how to do it. And so depending on which way you use, you might get a different result. There is also some people might say, okay, I don't want to do pixelated source. I want to say that maybe not this lens, but some other source might look like a Gaussian. And it also gives you a different lens model and source model, but they measure the data very well. So there is a lot of degeneracies. The nice thing is that, especially for lens model, different techniques typically agree on the lens model parameters. And the reason for that is, for example, in this lens, you have these 4 very bright images and an extended Einstein ring that gives you dozens of constraints. Even with a very complex lens, if you want to reproduce this image morphology, there is not much way how you can tweak your lens model around. And actually, RxJ1131, some other lenses I'll be showing, have been modeled by different groups using different data, different techniques. And lens models agree normally very well. Source models depends. If you go to very high resolution data and you have a lot of source structure, then again the number of constraints gets very high, and then the agreement between different models gets better. The main issue is when I would have low resolution or low quality data, because then the number of constraints is low, and you can fit a lot of different models to it. So there was HST. There is a second type of instruments we can have. So HST or any optical telescope, at the back of it is a CCD. Basically, at the back of it is an array of pixels that measure number of photons that strike them. Radio telescopes or radio interferometers don't work like that. So radio interferometer, what it does, instead of having a CCD at the back, it measures the so-called correlation function between each pair of antennas. And I don't want to go into math, I can do that later if you want, but what it basically measures is the Fourier transform of the sky signal. So all the nice images from ALMA that you see is not what actually ALMA measures. You need to use some heavy post-processing to create them, and heavy post-processing. The signal is a Fourier transform of the sky. You apply inverse Fourier transform, but there is a lot of information loss happening, so we have to be extra careful there. But actually for RxJ1131, we did ALMA observations of it, looking at a CO2 to 1 line. So this is a paper by Danuta Parafidze and me that came out last year. And in a CO2 to 1, which is tracing molecular gas, you see this very nice Einstein ring. Here are the 3 quasar images, but now seen in radio wavelengths. And this is an emission line, so there's some velocity structure, so you can basically map the velocity of the gas in this, and you see this amazing, I really like this image. So you see this amazing velocity structure in it. If you would look only at this part, there's basically a nice rotation going on here. This part goes to the red, this moves away from us, this moves towards us. So I actually did my PhD developing techniques like this and combining them with pixelated models. So we were the first ones to do that. And when you take the RxJ1131 and you do the reconstruction of the velocity of the emission line, velocity channel by velocity channel, this is the image you would get from ALMA, and this is the source planar construction. And you see there is a, if you know velocity curves, you have these nice kind of fishtail structures, which indicates this is a rotating disk. So I'll just let this play for a bit. The lines over here are the caustics. You might have seen, remember from yesterday, there's this diamond caustic for elliptical lenses. There's the outer caustic over here. So what is inside of this caustic will have 4 images. What is in between will have 2 images. What is over here will have 1 image. And the thing over here is because there is a second galaxy that is also doing the lensing. And so when you add all of these channels together, you get a massive gas disk. This dimension is 15 kiloparsecs, and this is the velocity field. So you see there is some pretty ordered rotation. Again, if you want to believe your data a bit too much, I wouldn't. This looks almost like a bar, and there is sort of a spiral arm over here, maybe another spiral arm over here. And if you have the HST data, so with Sherry Suyu, who did the model I was showing before, we combined our 2 models. And so this is how it looks like. In the black, you see the HST emission. So this is stars. The super dark spot here is the AGN, the quasar. And the red contours is the CO 2 to 1, it's the molecular gas. So now we see the gas, from which the stars form, the stars, and also the quasar, the supermassive black hole in the center. So if you want to do this yourself, there is different groups have been developing different codes for a long time, and this is just a very short list of what is available out there. One of the issues we are facing as a field is that a lot of codes are private, not open source. The open source codes are highlighted in blue, and they often offer limited functionality. You might not be happy about that. I'm not super happy about it either. Some people would say that developing a code takes really 3 or 4 years of your PhD. So if you want to actually develop the code and apply it to some data, you want to keep it to yourself for a bit. But a lot of these people are actually, if you write them, they might be happy to share or to collaborate with you. So for tagging, this is the first method where you pick your parts of rabbits. Gravlens by Chuck Keaton is an open source code that is very widely used. If you want to do more complex models, for parametric source models, you have a Lenstronomy by Simon Birrer. There are also some models that do pixelated sources. There is the Lens tool, which is widely used, and the newer thing called AutoLens that I will describe in a second. Lots of development in non-public codes. There's a number of codes for interferometry. So we have codes that assume that the source is a Gaussian or a Sursic function. Publicly available is VisiLens. There are a few more codes that are private. And for the pixelated models, for interferometry, this is the really hot area. Currently, there is no code that is publicly available. So I did one. Yashar Hazaveh did a massive upgrade of his code over here, which then formed into VisiLens. Simon Dye has a much updated version of his code, and there is some group in Cardiff, I believe.
Sure.
Yes?
The previous slide, those like diamond shapes are they are lens regions.
Yes.
Why are both different?
You mean here and here?
I mean on the inside, the rainbow shape and the one that's a little bit behind.
This one?
Right.
So what we have here, we have two lenses in Galaxy. There is this. I wonder if you see it in the image. Okay. So there is a main lens, there is this massive elliptical galaxy over here. But you see there is a small little point over here. There's a small satellite galaxy. And it actually turns out that the positions of these four images and the Einstein ring are a bit sensitive to what this galaxy is doing. So in caustics, they add in a very nonlinear fashion. But the small effect of that tiny galaxy is that over here there is a region where you will have. Now I wonder if it's 4 images or only a single image. But I think this is a region where you might expect a single image to happen. So you move from 2 images to 1 image, but the exact location of this and the size is actually difficult to constrain. So the constraints on the main galaxy are extremely good. Constraints on that small galaxy up there are much weaker. And actually what happened when we did comparison between between my data and a newer lens model from CAC, we couldn't agree on the position of that small galaxy and how massive it is within like 5 or 6 sigma. It was a bit unfortunate.
Doesn't the region of the satellite galaxy also have a diamond shape?
Because it's completely dominated by the by the effect of the main lens. But yes, you are right. Directly underneath it, there should be a small diamond caustic. Most likely what is happening here, let me see. So it's over here, that's about 0.3 arc seconds to the top. 0.3 arc seconds to the top is about, it would be somewhere here, but when we were calculating the caustics, you have to do it numerically, so it's probably not resolved in the calculation. That might be the case. That's a very good point. So the problem we are having with all this lens modeling is that all of these tools right now, apart from the alt lens, I'll explain in a second, need a lot of manual attention. For tagging, you need to find the parts of your rabbits. For everything else, you need to decide on the priors on the lens. And the issue is what is happening in 2020 is where big surveying instruments, the LSST, Euclid, and maybe SKA, will deliver tens of thousands of lenses. And you can't do them by hand. Just to put this is a SLAC sample we'll talk about tomorrow. 60 to 70 lenses found in the SDSS survey, which took like a couple of years to follow up. Keep this sample size in mind. This is the SLAC sample size. Okay, you can't see. There is thousands of galaxies that we will find using Euclid in 2 months out of 66 months of the mission planned. That's also a propaganda by the Euclid Consortium. So if this expectation holds, we will have massive problem to do the lens modeling by hand. What will most likely happen, we'll start selecting only a few interesting lenses that might have high magnification, but you still want to have sort of a preliminary lens model for them. And so the challenge is to modeling these lenses in bulk. There was an AutoLens by James Nightingale and group in Nottingham and Durham, where they tried to automatize this process as much as possible. So here you have, they need to model, they take an image, they make you can't see the Einstein arc here, here's the foreground galaxy, they subtract the galaxy, they have the model image, they get the source reconstruction. It works. And there's maybe more towards what MJ is going to talk about next week. In 2017, Yasser Hazava had a Nature paper where they used neural networks to not even do lens modeling, to use machine learning to find appropriate lens models. And here is some of the lenses, real and fake, that they analyzed. So this is how we do lens modeling. And now we would actually like to use it to put it to practice. And I'll start talking about what we can do with the sources. So just to remember, as we saw yesterday, as we saw the last 2 days, magnification is the ratio of an image area to the source area. So the total flux of the source goes up is proportional to magnification. The resolution, if you think of area as a circle, is proportional to the square root of magnification. And the exposure time to get the detection, let's say 5 or 10 sigma, goes as 1 over magnification squared. And some of the most spectacular results I'll show are coming from galaxy clusters, which is not something we really discussed a lot last 2 days because they are super complicated. But the point is, as we saw yesterday, when your source is located on the caustic, it makes this nice, if your source is located on the caustic, it will make this nice extended image. And clusters are huge in size. So the area over which you can get extended high magnification images is large. Downside is the clusters are very rare. But this is one of them. This is 20 arc seconds. This is a single lens galaxy, some 15 arc seconds across. And if you have a low resolution telescope, you can resolve this in massive detail. And I'll show you just one example. Okay, this didn't work very well with the projector. So what you should be seeing here is a massive blue Einstein ring over here. And at the very end of it is this blue spiral galaxy. What is happening here? This is a spiral galaxy that's lensed, but this is still a very magnified image. And this is the same thing stretched into an Einstein arc. As Eva Woutz noticed, this is one of the brightest things ever. It's also very extended. 10 arc seconds over here, this is 20 to 30 arc seconds. Okay, and you can't see it. If you would go back and look at the old photographic plates, you see an arc over here. This is a photographic plate, still done, the old school type on glass from, I believe, 1980s. And there's a bit of an Einstein arc here. The scales are not the same. And, that's where your eyes should be looking. So when you do the lens modeling, and this is a cluster with lots of galaxies in it, so it gets super complicated. We can't get the lens models to a high precision, but we can do a decently good job. So if you try the tagging approach, you should see a lot of labels over here. These are where they put IVU units to get resolved spectra for each pixel. Here is another image of the galaxy, and when you do the delensing, this is how your galaxy looks like in stellar continuum emission. There are these massive concentrations of light. This is in H alpha emission. which traces ionized gas and star-forming regions. This is the velocity from the H-alpha line, and this is the velocity dispersion. And that's pretty crazy. And you can do, you can take another lensed arc. So just this one. So this one is, I think, the one you saw before. And you see this massive Einstein arc. It actually makes 1, 2, 3 images of a single galaxy, as in arcs J1131, where we have 1, 2, 3 images. And you see a lot of these dots. Now, when you do your reconstruction, this is what you get. And these small dots turn out to be very compact star-forming regions. I didn't put a scale in it, but this would be on the order of few tens of parsecs. And the galaxy which is lensed is at redshift 2.5. There is another very nice arc over here, which is, I think, was my very first slide of a gravitational lens in this course. And you see this massive Einstein arc over here, the cosmic snake. Here is a star, which is showing the PSF features, the cross and some blurring. There is a lot of small arcs all over the place. And the magnification over here is on the order of maybe 100. So this is all done with HST, where we are looking at starlight. As we said before, ALMA, or at millimeter waves, we can do dust, and we can study the gas content of these galaxies. And so ALMA was trying to do gravitational lenses from its very beginning. Tomorrow I'll explain why. And these are the early days of ALMA. So blue light is starlight, mostly from lensing galaxies, and you see these red things over here. This is lensed dust emission from very high redshift galaxies, between redshifts 2 and 6. Sometimes you see a very bright lens. In this case, we don't even see the lensing galaxy. And this particular source, the red thing, is redshift 5.6. There is some nice Einstein arc here, nice Einstein arc here. This is hard to see. So these are early days of ALMA. ALMA has been adding more and more antennas, going to higher resolutions. So this is what it can do in the full resolution, the SDP81. Just to put this into perspective, because my scale fell out of the screen, the radius of this lens is 3 arc seconds. The nominal resolution of the data is about 15 milli-arc seconds. Just to talk a bit about this, because I spent a lot of my life on this. So SDP81, the source is at redshift 3.04, and it was targeted in 2014 by the so-called ALMA long baseline campaign, which is the first time ALMA went to the longest baselines and provided the highest resolution it can get. So the baseline up to 13 kilometers, they used multiple bands with lots of observing time. This is a lot for ALMA. They got 1, 2, 3 CO lines and a water emission. All the data was released public to everyone in February 2015, so there was hard time of a year because we wrote a paper in 3 weeks. There is a lot of ancillary data from HST, high resolution images. There is some VLA observations. These are some details of the lens modeling. We had to downgrade the resolution of the data because it looks amazing, but you realize that the signal on the longest baselines is super low. But even then, we get a typical resolution of 50 parsecs in continuum and in dust, and 100 parsecs in CO. And there is other groups that did the same modeling procedure. And back to your question, the lens model is basically the same within 1 or 2 sigma, and the errors are really small. And the source model actually also looks sort of the same. So we get it to high precision because we have super high resolution data. So this is how it looks like. This is the source reconstruction in band 6 continuum, band 7 continuum. This is all dust emission. This should be saying 1 kiloparsecs, except it fell over here. So this is 1 kiloparsec with really exquisite resolution. This is how it looks like when you lens it forward. And when you compare it, when you take this and subtract it from the data, you can't see any structure in the residuals. We really captured all the complexity of the source. There is no blobs poking around here. So this is dust continuum. These are the two CO lines. And I'll just try to flick. So here in dust continuum, we have these 3 distinct blobs. You kind of see them in the CO5 to 4. You don't see them in the CO8 to 7. For these 2 lines, we also have good enough signal-to-noise ratio to the velocity and velocity dispersion maps. So you are welcome. This is the velocity field in CO5 to 4. Also in 8 to 7, this is the velocity dispersion map. It gets very high in the southern part of the source. And that is not because if you would take a velocity dispersion from a Gaussian, it's not because we have a super wide Gaussian. If you look at the spectrum, we have 2 blobs. So when you try to do velocity dispersion from that, it's something massive. Which means there is most likely an infalling gas into the lens. We added more data. This is another another continuum data set, C2 emission, CO3 to 2. And in the paper we submitted a few months ago, we combined all of this together. So this is how the source looks like in far infrared, the dust, CO, C2. When you overlay it, you see that dust is compact, CO is a bit more extended, C2 is very extended, and actually if I would zoom out, it goes much higher in the direction. And so we make this very nice image. What do we do with it? We can use radiative transfer models, because what this comes with, for each part of the source, we have several CO lines, C2 line, and far infrared continuum. So we can use radiative transfer model to model the properties of gas and dust in each part of the source. And for example, if you do this for the far UV field from stars, you get something like this. So there are some 2 peaks. So the black contours is the dust brightness. And you see the 2 points where the dust is the brightest because it's heated up by intense star formation. Also the far UV field from newborn stars is the strongest. There is some structure in the gas density, and the errors on these parameters are actually super low. Some people push this a bit further. So remember the cosmic snake lens that I was showing a few slides ago, this massive thing. There was a recent Nature paper by Desauge Zawadzki. So here is the big Einstein arc, if you zoom onto it. And what they did, they used ALMA to study, I believe, CO322 emission in it. And so what they do is they found a lot of distinct molecular clouds, again at very high resolution. So you now really can study these in detail. Just to show you how you found these arcs, these clouds, here is the velocity structure of the gas. But when you go through it channel by channel, you'll see in the I think this is the reddish channel, there is some blob over here. And as you move in channels, there is some clouds will appear, and then they disappear because they move out of the velocity structure. Some of them are super bright. You see 1, 2, 3 clouds together appearing over multiple channels, and this continues further. And this is an amazing data set and shows what you can do with ALMA. Again, making pretty images is not enough. We want to do science with that. So what they look at is at the sizes of the molecular clouds. These are shown in purple, and compare them to what you see in the present-day universe. And also, because they have the velocity structure from these maps, they also get the velocity dispersion for each of these clouds. And you see that they have much larger velocity dispersion than those seen in nearby galaxies, but comparable to those what you would see in the nearby star-bursting, intensely star-forming galaxies. which is a very nice result. So this is when we go to very high resolutions. We can also do a step back and say, I don't want to have a very high resolution galaxy I'm going to be able to see anyway. I want to look at super distant galaxies that are too faint for us to see normally, but because of the gravitational lensing, they become brighter. And so we keep on hunting for the most distant galaxies. Okay, this is going to be hard to see, but basically what people are trying to do, they try to look for massive clusters that provide a lot of magnification, and then take very deep exposures in different colors, and try to look for something that's super red. Super red most likely means very high redshift, or you just got unlucky and it is a very red galaxy. But there are some more sophisticated techniques how to do this, and so that's how this redshift 9 galaxy was found in 2012. You can't see it very well on the projector, but there's a lensing cluster over here. If you look into this field in detail, you should see a small red dot over here. If you zoom in further, there's this very small red galaxy that existed only a few 100 million years after the Big Bang. It gets better. You can do redshift 10. So this is okay. This is another lensing cluster. There is a small red thing over here. If you would zoom in, you see this reddish thing over here that you probably can't see on the monitor, on the screen. That's the redshift 10. And you can do even better. You can go to redshift 11. And this is one of these extreme clusters. What you see here are the critical curves for different redshifts. And then, where are we? And then what they found is actually there are 3 images of a single galaxy that appears to be at redshift 11. Is this the most distant galaxy we know about? No. Sorry?
How do one see those images and say, hey, those were the same galaxy?
Data processing. Or basically what you do is you have lots of different narrowband filters. So you try to do this from the spectrum of these galaxies. And doing spectroscopy is very expensive over such a wide field of view. So what people are aiming for is when you have the continuum. So this is your wavelength. This is intensity. And I'm not a person who works on stars, so I'll just try to sketch this very briefly. There are few. If you look at the star continuum, there will be 2 jumps in it. There is a Lyman break, and there is a Balmer break, and this comes because of an absorption by intervening gas. And so how this is done, you would take narrowband filters that are sensitive only to color over a very narrow range of wavelengths. But it's still not spectroscopy. It's just a few of these. And now when you would take this galaxy and consider this filter, you see something super faint. Here, you see something super faint. Suddenly here, you see something very bright. And here you see something very bright. And this is actually what they did here. So you see infrared color in 3 different filters. I didn't know which ones. And so this can already allow you to weed out, to basically remove things at low redshift reasonably well, but then you still need spectroscopy. The problem with these galaxies is often, even for spectroscopy, they are very faint. So some of these have unconfirmed redshift. That's a problem we have. There was a. I still have half an hour. So there was a push to do this a bit more systematically rather than people looking at their favorite cluster. So what people did was the so-called Hubble Frontier Fields project. So some of you might know Hubble did few ultra-deep fields where they just look at some patch in the sky and integrate forever on it. And some of the widely shared images of these nice images full of galaxies come from that. What has been done here is that people decided, okay, let's look at galaxy clusters and observe them for a very long time to bring out very faint galaxies. And also because these are lensing clusters that do lensing, we'll also have additional boost from the lensing magnification. So here is a selection of 4 of them. And just for comparison, it also looked at similar fields without lenses in them as a control sample. And so here are again, here is one of the clusters, ABEL 2744, you can't read that. Here is its control field. And on this monitor, on this screen, you can't see much lensing here, but there are some arcs happening around. There is another cluster targeted by this, ABEL 370, and here you see the cosmic snake. And the problem with the clusters is that they are very complex. And so if you find, let's say, the galaxy we had here, so we have 1 to 3 images of this galaxy, but you want to know what is its magnification. Now, this would be easy if there was 1 or 2 galaxies doing the lensing. These clusters have dozens of galaxies in them, and the dark matter distribution is complicated. So what the Hubble Frontier Fields team did, they had separate teams that were doing lens modeling for each cluster. And here are some results for ABEL 2744, a team led by Marusha Bradac. And what you should see here is that the red curve shows the positions of the highest magnifications. And you see there are some pretty strong differences. Like overall, the shape is pretty fine. Like it has this like 1 big blob, second big blob. Here they use much more complexity, so it gets much more complicated. These are still being continuously adopted. There have been some challenges where people try to do some predictions and see which of the modeling techniques works better. But this is the systematics we have to deal with clusters. You can't, making the lens model, even if you use the same data, look similar is difficult. So I talked about very high resolution. I talked about going for very distant galaxies. Now I'll talk a bit about going for very faint, not galaxies, but spectral lines, such as water. So water is not only on planets, it's actually in the interstellar medium and lots of it, but water emission is very faint. And lensing is an ideal tool to make it, because you have the extra boost, flux boost for the lensing, you can still use strong lensing to detect this emission and even start resolving it. So this is an older paper from 2008. It was a Nature paper by Impellitzeri, where they found water in this high redshift quasar. People have been doing it also in normal star-forming galaxies. So this is water emission from galaxies from redshift 1.5 to 4.2, taken with a Plateau de Bureau interferometer, now called NOIMA in France. And if you combine all the lenses together, this is done from very early ALMA data from strong lenses from the South Pole Telescope sample. You see this, if you stack the spectra, you see these loads of spectral lines here. There are some super bright ones like the CO, which is what we could observe without lensing. But there are all these other lines like C1, CN, HCO+, another CN, maybe some water lines that are detected. And by having a lot of these weaker emission lines accessible for lensing, we can really understand these galaxies and the physical processes of them much better than if we are limited to few very, very bright lines. Moving a bit to the issues with lenses themselves. So I've been showing you all these nice ellipticals. Now I'll show you a spiral. So spiral galaxies are not our normal lenses, but they show the issues we might be having as well. Because there is a supermassive black hole, both in spiral galaxies and elliptical galaxies, the galaxy, your lensing galaxy might have some disk or some substructure. Often, if your imaging is not deep enough or not high resolution enough, you actually are not 100% sure if there is no disk or if there is no additional stuff floating around. They have stars, and as we saw in previous lectures, stars are point-like masses that behave like lenses. They do lensing, and actually do microlensing as well, even at very high distances, and we need to take this into account. And finally, as I mentioned before, there is dust in lensing galaxies, which can dim your lensed images, because if your light passes through some dust, it will dim down. But maybe the big issue we have with lensing galaxies is that I've been misleading you a bit. Do you remember this exercise from day one, where we have this infinite sheet of uniform mass density, and when no matter where your source is, the rays go through unperturbed. They just go straight. So now we have the lensing equation, where this is our diffraction angle, which is the gradient of lensing potential, and your lensing potential, sorry for the capital here, is just the integral of your gravitational potential. What this infinite sheet of mass does, it adds a constant to the potential, but the constant is completely lost in the gradient. So I can have a lens that's singular isothermal ellipsoid or singular isothermal sphere, and I can add as much mass to it, as long as it's uniform across the entire lens, as I want. So how do we measure the masses of galaxies? Like, what is this? So this is a well-known problem, the mass sheet degeneracy. But the problem is that, sure, for most of the lens modeling, we assume that the lens is singular isothermal ellipsoid and nothing else. But we cannot exclude a constant mass component from just modeling the lens. We need something else to constrain the mass if you really care about it. So how we can do it? One option is to use the time delay, because the gravitational time delay is proportional to the absolute value of the potential. So here we have the gradient, and if you add constant to the function and then take a gradient of it, the result doesn't change. But the absolute value and the time delay will. So we can somehow measure the time delay between the different images of the lens. We can break this degeneracy. And the other option is, we know how to weigh the galaxies. We do it all the time using kinematics. We have the velocity curves, we have the velocity dispersion. For even nearby galaxies, that's how we measure their mass, because that's sensitive to the 3D mass distribution. So some of the more challenging techniques are doing a combination of these two. Because if you observe a gravitational lens, you have a probe for how much mass is enclosed inside the Einstein radius, and this is a slide I stole from Matteo Barnabé. But what you can do resolved spectroscopy of the lens galaxy, and then gives you 3D velocity, and it gives you the velocity field and the velocity dispersion, which tells you something about the mass profile of the lens. So you have suddenly two independent constraints. And what people like Matteo have been doing is trying to combine these two approaches into a single consistent model. Now that's very difficult, but you can do it. They did it for some of these more elliptical lenses where you use velocity dispersion. But you can do it for some galaxies that look more like some lenses that look more like spiral. So what you can see here, there's this disk galaxy, bright nucleus. There's disk. And then there is this faint thing over here, which is an Einstein arc. It's not a massive galaxy, so its Einstein radius is small. Its Einstein arc is close to the center of the galaxy, but it is there. So what they did in 2011, 2012 is use the lens image and then go to Keck, the big telescope on Hawaii, that has an integral field unit that takes a spectrum for each pixel of the image, and observe the velocity field of this galaxy. And so when you do the joint analysis, you basically reconstruct the source from the normal lens modeling, but you also, for this galaxy, you have nice resolved gas and stellar kinematics because you measure these from your spectroscopy. And so this is a very nice technique that allows us to break all of the degeneracies and put even better constraints on the galaxy masses. And crucially, let me go back to the slide. This allows us to do something pretty fancy here. Because gravitational lensing only tells us roughly how much mass is enclosed within the Einstein radius. But stellar dynamics is sensitive to the resolved, to how much mass, basically with stellar dynamics you get a probe of how much mass is enclosed as a function of radius. So here you have a single measurement. Here you have that measurement as a function of radius, right? Because the rotational velocity is proportional to the mass enclosed. So this is a nice way how to test the mass profiles of galaxies. And speaking more about lenses, there was a question yesterday, and then that I kind of led you again that I didn't focus on yesterday. What happens to central images? Because yesterday I was showing this picture for a single isothermal sphere, and in principle, you can form. Okay, let me actually take it this way. No. Think about the Mexican hat. I was mentioning yesterday that tells you that it's an approximation of the time delay surface. And the problem I was mentioning yesterday with a single isothermal sphere or ellipsoid is that as you increase your radius, your mass goes to infinity. But the other problem happens in the very center, because your density is proportional to 1 over r squared. So if you set r to 0, your density goes to infinity. Well, that doesn't happen with stars or dark matter. You can't get infinitely high density of stars. So what you often do in practice is that you say, okay, I want to get rid of this singularity in here. I'll modify this term a bit. And what this corresponds to is so what happens now is that you have your radius. Here is a 0, but a single isothermal sphere, density goes to infinity. But you say no. In the center, I might have a bulge or something or some compact star there is going to be another density profile parameterized by this core radius, which is non-zero. It's the size of some central mass, central density component of the galaxy. So even if my R goes to 0, this doesn't go to infinity. And so what this means is that you get rid of the singularity in the single isothermal sphere, and you can form the third image in the time delay maximum. It's going to be super faint, because all the photons will say, oh, I want to go to here or here because it's faster. But the probability means that some of them will end up over here. And that would allow you now to probe how much mass is in the very centers of galaxies. So people have been trying to do this for decades. And what we ended up with so far is one confirmed central image. This is from the global VLBI 15 years ago. We didn't get any better since then. So here are two, A and B are two super bright images of a lensed AGN. They look great because they are done in a contour plot of sigmas, and the signal-to-noise ratio here is crazy. And then if you look very closely, there is this small blip over here, which is a central image. Very faint, but it is there. So how come that in all these things, in all these approximations for realistic galaxies where we put in the core radius, I form a central image. Okay, it's very faint, but I'll observe long enough. I should find it. And we found one. It's because there is actually a singularity in the center. There's a supermassive black hole in the centers of these galaxies that actually allows you again to have a density going up to infinity, because it's loss of mass really now in a single point. And this is how you can get basically physical singularity in the center. What happens over there, such as in the Event Horizon Telescope, is much more complex. It's beyond the ray approximation we are doing here, and I'll skip this, and I won't talk about this in this lecture. This is where I will stop for today. Thank you very much. So for those of you who came later, there is an exercise sheet for day 3 on the Google Drive, so you can use the usual link. I'll put it up in a second to access it. I'll be leaving the tutorial, unfortunately, a bit earlier, around 3:30. And I won't be here in the afternoon, but I'll be here from tomorrow morning, 9 a.m. For those of you who have questions, I'm sorry about this. Yesterday, we had some discussion on the solar eclipse problem. I uploaded the discussion of whether you need the lensing correction or not. And if you don't mind, what we can do at 3 o'clock, we can have a short, I might ask you to discuss the solar eclipse problem once again, because I think it's one of the more interesting exercises, as you are really redoing one of the big papers in the field, and discuss how are we getting the solutions, and whether we can tell the difference between Einstein and Newton. Thank you very much. Yes, I made a mistake in the equation here. So I put in the equation for the potential, but what you need to consider is the full time delay surface. And when I get the pen, So there you need to consider the full time delay surface, and I, by mistake, dropped the first term here. So your function t x y is going to be the potential that is given there, plus, and now indeed the distance between the image where it formed and the source, where in this case, so in general case this would be source position, image position minus source position squared, but we set the source to 0. In this case, as it's stated at the beginning of problem 1, or of the task 1, so you only need to add a term that is x squared plus y squared, where x and y are the position of the image you are considering. My apologies for that, I'll modify the sheet. We're only considering the second term here because all of this is just the constant. Theta is the image position, beta is the source position which we set to 0. So the full equation for x, y position of the image is 1/2 x squared plus y squared minus the potential. If I can interrupt you for a moment, as I'll be leaving in about half an hour, I thought we could shortly talk about the problem we did. That was last problem from yesterday, the solar eclipse of 1919, and whether we can use the actual observations to distinguish between Newtonian and Einstein's predictions. So I brought up again the table with the data. So here are the 13 stars detected in the plates. This is the magnitude of each star, we don't care about that. This is the position of the star if there is no eclipse and there is no gravitational effect. And your task was to use these positions and the mass of the sun, which we know, to calculate the predicted deflection angles for Newton's and Einstein's cases, and compare them to the deflection angles observed in Brazil and in Africa, and see whether we can distinguish between the two theories. So what I can do, I can bring up a table. I'm not sure if you can see the table decently clearly. So I didn't put in the names of the stars, but I just went from the top of the table and numbered them 1 to 13. So the first part of the exercise was that the positions of the stars were given not, you weren't told the total offset from the sun, but the offset in the x and the y coordinates. So the sun is over here, and basically you have the x offset, y offset, and they were coming in weird units of 50 arc minutes for I don't know what reason. So if you, as a first check, could you give me the values you got for if you have the values for the distance from the sun, can you give it to me for a few stars? Or if you only have calculated the deflection angles, we can move to that part as well and see where we stand. Okay, so I decided to go ahead and quickly do that. So what I did here was I copied the position of each star in units of 50 arc minutes. So this, if you would check it compared to the table, I hope you will see the same values. If not, I made a mistake. These are the same offsets, but along the y-axis. So just to make that clear. And then all I had to do, you can't see it here, but basically take this number and convert it into arc seconds. So this is in units of 50 arc minutes, so just you multiply it by 50 and then multiply it by 60, and you get the distance in arc seconds. Along the x-axis, the same along the y-axis, the minus sign merely means that your star is above or below the sun, or to the left or right. And then you simply add them in quadrature and take the square root. So this should be the distance from the sun. I'm not sure if you were getting similar values in general. As a sanity check, Does anyone know how large the sun is in the sky, roughly?
30 arc minutes.
Sorry?
30 arc minutes.
Yeah. So the diameter of the sun is around 30 arc minutes, which is around 1800 arc seconds. So its radius is around 900 arc seconds. How did the first star make it into the table? It's not completely clear to me. It's actually for one of the observations it should be lost in the corona, but or basically this should be coming from one of the early exposures where the sun might have been still moving into the, or the moon was still moving in front of the sun, was still going to eclipse the sun. So they took a number of exposures and could calculate even the deflection for stars that would normally be behind the sun. But for one set of observations, it's almost lost in the corona. And so now the question is, what are the actual deflection angles? In case you want to calculate them quickly, just remember that the Newtonian prediction was that the deflection angle was going to be 2gm over c square and the distance to the sun. And the Newtonian, and Einstein's prediction is 4gm over c square r. So there is you should now have all the information you need. And if it would be possible having units of arc seconds, would be great. Okay, we can do one more, and then we can compare with the results. What you can also see here, I mean, you see that the calculation is going the right way. For the star that's the closest, the deflection is the largest, and then it goes down with the distance. So this one is further away, this one is much closer, this one is a bit further away again. So I'll just highlight the relevant units here. So the mass of the sun is 2 times 10 to the 30. There's the gravitational constant in meters, kilograms, seconds, and 1 AU should be 1.5 times 10 to the 11 meters. And this is, okay. So basically, with all of these, the only issue is converting radius into is converting this angle into radians. So we have now estimates of the angle for 4 stars. I'll just move to, oops. So these are the measurements from Sobral. I can try to make them bigger by a factor. So unless I messed up something when copying from the table, this should be the oh, thanks. Yeah, I'll turn the, no, it's tricky. No, wrong. So let me try to make it even bigger, so that might help. So the displacement of the first star was about 1.3 arc seconds. You should check this for me. So what I'm just doing is adding these two in quadrature. The displacement for the other star is 0.85, 0.9 versus 0.9. Are we missing a factor of 4 somewhere? Or 8? Or was I not noting the numbers down exactly? So what I will do, I'll leave you with this issue. You should have all the tools to do it, so there's no need to do gravitational correction when calculating R. and we know that the sun is 1 AU from us. We need to convert this into, the angle into radians again, and there is GM, M star, and 1 AU. We know how large they are. What I will also do, tonight, let's say, I'll post this table on the website, so you can also go through it and see if I made a mistake. What I wanted to, it might well happen. What I tried doing here was to, okay, I hid it from your view. Oh, okay. Now the formula doesn't very big because I added some more columns, but at least I was getting pretty good agreement with Einstein prediction, which makes me feel more confident about the result. So I'll post this on tonight, and please go through it, and we can discuss this in more detail tomorrow. Just before Esteban drags me, thank you to all of you who signed up for the paper presentations. If you have any questions, just email me. I'll also try to look at the papers you chose and let you know if there is something tricky about them. There shouldn't be anything. And tomorrow we will have exercise again at 2, as usual. If everything goes well, we can discuss this problem and the problems from today. If you have any questions, email me. The plan would be for tomorrow and for Friday to try to do an exercise on computers with Python or Excel. We will try to, so now we are doing a paper from 1919. What we will cover in the lecture tomorrow is how we find gravitational lenses. And what I will try to do with you is to find gravitational lenses in an existing database from a survey with a very large array. So we will try to repeat some of the steps that we will cover during the class and see if we can also find some gravitational lenses in it.